Okay, guys, we're going to go ahead and get started with our elastic potential energy notes. So let's talk about what elastic potential energy is. And we're going to define elastic potential energy as the energy that is stored when something elastic, like a spring, rubber band, or ball, is stretched or compressed. So here we have a ball, and we're going to show what happens right as we drop this ball. It hits the ground. Once it hits the ground, though, it's going to compress, just like we can see here, and then it's going to bounce back up. So if we were to think about this in terms of energy and energy bins, we would show that in the beginning, right, at this point right here, the ball has some kinetic energy because we can see that it's moving, and also some gravitational potential energy. The ball is not stretched or compressed at like point A, I would call this, because we can see that the ball is fully round. So we're going to have some of each of those, but no EPE. At the bottom down here, we can see that the ball has no height anymore, but it's still moving. It's not stretched or compressed, so we should only have KE at this point. Next, over here, we notice that we don't have our movement lines anymore, so we're no longer moving. We notice that we're at the ground, so we no longer have height, but we see that our ball is compressed. Because our ball is compressed, we're going to have some elastic potential energy. And then lastly, over here, we see that the ball is moving upwards again. So we notice that we have the movement lines. We're going to have some kinetic energy, and then we have some height, so we're going to have some gravitational energy. We notice that the ball here is lower than it is at this point, so that means that our GPE is going to be less over here relative to where it was in the beginning. So now let's dive into the components of elastic objects. And we're going to say that all elastic objects have a natural length, we'll abbreviate as NL. And this is the length of an object when it is not stretched or compressed. So in other words, there's no elastic energy that's stored in that object. The amount a spring is displaced from its natural length is given by the variable x, which just means distance displaced. So if I were to stretch a spring, it would have an x distance from that natural length. If I were to compress it, same thing. And let's take a look at that real quick. So right here, we can see we have an ordinary spring. It has some natural length. And over here, we see that we are compressing this spring. So we're taking this spring and we're pushing it inward, meaning that we are compressing it a distance, and that's what this x variable stands for, how far we compressed it. So if this is our natural length, we can see that we've compressed it this far. On the flip side, we can also stretch it. So this is still our natural length, but this time we are stretching it, so the distance stretched is going to be this distance right here. Okay, so now let's talk about the equation for elastic potential energy. And that equation is pretty simple. It's just EPE equals 1/2 kx squared. Some of you might say, hey, this kind of looks a little familiar. Maybe the variables are different, but I feel like I've seen an equation before that's 1/2 a variable times a variable squared. Yeah, this equation is the exact same kind of format as the kinetic energy equation. EPE is going to stand for energy, which has the units of joules. K is the spring constant, and we'll talk about that in a sec. But the units of the spring constant is going to be newtons over meters. And then X, like we talked about on the last slide, is the displacement from the natural length. And because it's displacement, it's going to be measured in meters. So like I said, the spring constant is going to describe how stretchy or stiff a spring is. The higher the K value, the more rigid or stiff the spring is. This just means that it's going to take more force to compress, and it's going to store more energy. And if we look at this equation, that makes perfect sense, right? If K gets bigger and bigger, EPE is going to get bigger and bigger. If K gets smaller and smaller, EPE is going to get smaller and smaller. Just saying that the bigger the K value, the more energy our spring is going to be able to hold. And now let's look at it from a force perspective. So the equation for force is known as Hooke's law, and that's just going to say that the force of a spring is equal to K times X. So F is going to stand for spring force, and we have to remember that force is measured in newtons. K still stands for spring constant, and X still stands for displacement. If we look at this equation right here, we said before that the higher the K value, the more force it's going to take. Well, that makes sense, right? If we increase K over here, force is going to increase. If we decrease K, force is going to decrease. Let's think about your pens, how your pens have springs in them, right? I have a pen here. So inside this pen, do you think that the spring constant is very big or very small? I would argue that the spring constant inside a pen is most likely pretty small because it's pretty easy to push down. If it was really big, then it would be very difficult to push that spring down, and we all know that's not the case. Let's take a look at an example really quick, and this is going to probably be one of our hardest examples. So this says a spring has a natural length of 0.245 meters. When a 1 kilogram mass is hung from the spring, it stretches to a distance of 0.61 meters. How far will the spring stretch when a mass is dropped from the natural length? So let's go ahead and draw a picture. And here we have our spring that's just hanging from its natural length. And over here we have the spring once we've added that 1 kilogram mass to it, and notice that it's stretching a total distance now of 0.61 meters. So we are tasked with figuring out how far will the spring stretch when a mass is dropped from the natural length. So again, we need to remember that at this point, the mass is just hanging there. It's in equilibrium. So it's not moving, forces are balanced, right? We remember what that means, and we'll take a look at it later. But we want to figure out, what if we put the mass right here and just drop it? What's going to happen? How far is it going to stretch if it's just dropped from this natural length? So in order to do this, we need to figure out the K value using Hooke's law. So we said that this hanging spring is at equilibrium because it's just hanging here. It's not moving. So we need to remember that the net force is equal to mass times acceleration. If it's not moving, that's just equal to 0 newtons. Let's also look at this though. What forces are acting on this mass as it's hanging from the spring? Well, we know force gravity is pulling it down, and we know that force spring is holding it up. We just said that the mass is not moving, so these two things are equal to each other. So force spring is equal to force gravity. Perfect. So now all we have to do is plug in our variables to the equation. We get mass times gravity is equal to kx, because force spring is kx and force gravity is mass times gravity. All we have to do now is plug in our numbers. We know that the mass of the object is 1 kilogram. It tells us up here. We know that the gravity, because it's on Earth, should be equal to 9.8. And then we know that K is unknown because that's what we're solving for. But we also know what X is. X is going to be 0.365. Some of you might be asking how I got that. Well, again, X is the distance stretched from the natural length. If the natural length is 0.245 meters, and I'm stretching a total distance of 0.61 meters, X is going to equal the difference between those. So 0.61 minus 0.245. And that gives me an X of 0.365 meters. Next, all we have to do is solve for K. We find out K is equal to 26.8 newtons per meter. Alrighty, now that we know K, we can use energy to figure out the length of the spring when the mass is dropped. So here's our picture. This time we're going to drop this mass, right? And the mass is being dropped from this point over here and falling all the way down to this point over here. We don't know how far it's stretching because this is different than just letting it hang. Well, when we drop this mass, it's going to move down, and it's going to move back up and down and up, down and up, and it's going to kind of hover between a certain point over here. And that's our equilibrium point that we had before. But we want to figure out what's the maximum distance that this is going to stretch once it is dropped. So if we look at this in terms of energy, we can say right here, well, at this point, it's not moving. So at point A, it only has GPE. And then we can argue that at point B down here, at the maximum stretch distance, it also isn't moving. But what does it have at point B? Well, the spring is being stretched very far, so it's going to have a lot of elastic potential energy, which means that we can set these two things equal to each other. So we find out that mass times gravity times height is equal to 1/2 kx squared. Now comes the fun stuff, and this is something that a lot of people struggle with and have a hard time identifying. So let's assign an origin really quickly. And I'm going to say at the bottom down here is our origin, meaning that at the ground, our height is 0. Well, at point A then, our height is going to be some number. Well, look at that, right? If we're starting up here and we're ending all the way down here, this is our height. Well, our height is the same as our stretch distance. So that's really important. Because the height is the same as the stretch distance, we can replace h with x. We realize that we have an x on both sides, so we can go ahead and cancel an x out from each side. We're just left with mass times gravity equals 1/2 kx. We know all these variables, so all we have to do is plug in and solve. We find out that our stretch distance should be 0.73 meters, which is just telling us that the spring will stretch 0.73 meters from the natural length. And like I said before, the reason why our height and our stretch distance are the same is because we're setting our ground, right, our artificial ground, to be the bottom here, to say that there's no height.